In this part of the video, we're going to go over one of the fundamental theorem that is having to do with the angles related to a angle on the Euclidean plane. And it is called the inscribed angle theorem. The theorem says that the measure of an angle inscribed in an arc is 1/2 the measure of its intercepted arc. Well, I mean, you see, we're going to look at 3 different cases for the way with which the angle could be inscribed on a circle. Well, namely, we would be having the following 3 cases. In the first case, the center of the circle O is in fact on one of the edge of the angle. And in the second case, the center of the circle is in the interior of the inscribed angle. And lastly, in the third case, the center of the circle is in the exterior of the angle. So, well, but I mean, as we could see, what we are trying to show is that in all these 3 cases, the measure of the angle BAC is equal to 1/2 of the measure of the arc BDC. Well, so we're going to begin with the fundamental case, namely the first case. Now, in case 1, we are assuming that the center of the circle is on one edge of this angle. And let's try to think about what we really want to prove here. Well, in fact, by definition, in this case, the arc BDC, which is actually part of a semicircle, it will have to be a minor arc. Therefore, the measure of this type of arc is precisely the measure of the central circle facing this arc. Namely, in our figure here, it's the central angle BOC. And what we want to show is we want to show that the angle or the measure of the angle CAB, it is in fact 1/2 of the measure of the angle COB, because by definition, the measure of the angle COB is just the measure of the arc CDB. Well, let's try to see why it is the case. Well, the major reason, the major observation is we note that the line segment AO and CO are both radii of the circle, so they will have to be congruent to each other, which means the triangle AOC is an isosceles triangle, right? And consequently, we have the following observation. Note that the base angles of this isosceles triangle are going to be congruent to each other. Therefore, the measure of angle CAB is equal to the measure of angle ACO. At the same time, we observe that the angle COB is in fact the exterior angle to the triangle COA, with the angle ACO and CAO as the non-adjacent angles to this exterior triangle. So we have the following observation. where COB is an exterior angle to the triangle COA. As a consequence, the measure of this exterior angle is supposed to be equal to simply the sum of the measure of those two non-adjacent interior angles of the triangle, namely the measure of angle COA and the measure of angle CAB. The sum of these two angles is going to be equal to the measure of COB. But we observe that those two angles are in fact congruent to each other, so the sum is simply equals to the double of the measure of CAB. And we are done with the proof. Let's look at case 2. The proof of case 2 turns out to be based on the result from case 1. In fact, what we're going to do now is going to be linking point A and the center O and construct the diameter of the circle. And we're going to denote the other endpoint of this diameter as E. So now, by case 1, what we have shown is that when the inscribed angle has an edge as the diameter of the circle, then the inscribed angle is going to be of 1/2 in terms of the measure to the measure of the arc. So specifically, both the angle CAE and the angle BAE are of this type of inscribed angle. Namely, what we have had, we note that the measure CAE is equal to 1/2 the measure. Let's call it CDE, for instance. And for the sake of convenience, we're going to introduce the point F and observe that the measure of the angle EAB is 1/2 the measure, let's see, EFB by case 1. Yep, and on the other hand, we note that point O is in the interior of the angle CAB. Therefore, from a postulate of the SMSG system, we do observe that the measure of CAB is in fact the sum of the measure CAE and the measure of angle EAB. On the other hand, by theorem 3 that we have proved in the last video, the measure of the arc CDE plus the measure of the arc EFB would be equal to the measure of the arc CEB, which is precisely the same arc CDB. Hence, case 2 is proved. Lastly, Let's consider the third case, in which the center O is in the exterior of the angle CAB. Well, but the idea is similar. What we're going to do is just construct a diameter AE. So in particular, we note that the measure of CAE is equal to the measure of the arc CBE, for instance. And on the other hand, now O is in the exterior of the angle CAB. Hence, we have the following relation, that the angle CAB, or the measure of the angle CAB, it's equal to the difference between the measure of the angle CAE and the measure of the angle BAE. But on the flip side, we also have the following relation, which says that the measure of the arc CDB is equal to the difference of the measure of the arc CBE subtract the measure of the arc BAE. I'm sorry, the measure of the arc BFE. Yep. Yeah, right. I mean, so at the same time, let's also observe that you see the angle BAE is also an angle inscribed in the circle with the diameter AE as one of the edge of this angle. So we could also apply case 1 to conclude that the measure of BAE equal to the measure of the arc BFE. Hence, if we compare these two equalities down there with the relation that we have had up here, we could immediately conclude that the measure CAB is precisely equal to the measure of the arc CDB. And this completes the proof of this inscribed angle theorem.